What is the brain? You may be puzzled about this question because you expect to talk about the self. So you might rather expect the question, what is the self, rather than what is the brain? And as a neuroscientist, you may be particularly puzzled. You're not interested in what is the brain. You are interested in how does the brain function. And at best, how does the brain function that it is possible to generate or yield what we call self. But what is the brain? No. That's a question for philosophers. They ask what question. But from the viewpoint of the self, we might want to ask, what is the brain first? How is it possible that the brain, which is just a gray, pulpy device, and looks pretty gruesome actually when you see a dead brain, how is it possible that it can contribute to something what we experience of self? A sense of self, a subject. Philosophers have struggled and argued about these notions for centuries. Now, neuroscience more and more comes into the territory and explores what are the neuronal mechanisms related to the self. And that, of course, raises the question, what then is the self? Maybe the self doesn't even exist. Maybe there's just a brain. So, to address the notion of self, I first asked, what is the brain? And let me go back into the history of neuroscience. Neuroscience is a relatively young discipline, the mid of 19th century. And one of the leading neuroscientists at the end of the 19th and 20th century was Charles Sherring. He investigated mainly sensory motor functions. And he said that basically you get a certain stimulus and the brain reacts. Or the brain pushes out and you get a movement. So basically the brain is like a reflex apparatus, like the car or the bike in your garage. You push the pedal and the bike moves. You push the gas pedal and the car drives. But without you pushing either the pedal of the bike or the gas pedal of the car, neither bike nor car move. This is the way Sherring and much even of current neuroscience today, like cognitive neuroscience, who applies specific tasks or stimuli to elicit the function of certain regions, imagine the brain. So, for instance, you start with a particular stimulus. This is a famous painting by a Norwegian painter, Edvard Munch. The scream, you probably have seen it. I've seen it for some time in my basement when it was no longer in the Museum of Oslo. But then, before coming to Canada, I decided to return the painting. So, you see the stimulus, and this stimulus induces a certain activity in your brain. Here. This is called stimulus-induced or task-evoked activity. And most importantly, this activity is usually exclusively and completely associated with the stimulus. The stimulus is in charge of this activity. The brain itself is just a reflex machine, where the stimulus is in a reflex-like way processed. Meaning the brain itself has really no say in what happens in the brain. So your car has no say in how strong you push the gas pedal. Just push and then it drives. Same thing with the brain, like a reflex apparatus. As said, this is not only the past view of the brain, but much of that kind of view is still implicitly presupposed in current neuroscience. However, nothing without alternative. So the brain has also been assumed to be an active player. For instance, Graham Brown, a student of Charles Sherring, observed spontaneous activity in the spinal cord without any movement. No movement, but activity could be measured in the spinal cord. That is strange. Imagine you open your garage door and your car is moving back and forth. And your bike is moving back and forth without you doing anything. You say, this is crazy. Yes, that is when the brain is in active play. So now, you no longer start with the stimulus, But you start with the brain. Here you see the dark blue bars indicating the intrinsic activity of the brain, or also called resting state activity. So that term is rather paradoxical because the brain is never addressed. Your car is addressed. Your brain always moves back and forth. Yeah? So, and with that intrinsic activity, the brain approaches the stimuli, like the painting. And that in turn modulates the ongoing activity, and that leads to what is called stimulus-induced or task-evoked activity. That then is really resulting from a specific interaction between the brain's resting state and the stimulus. We currently only know that the brain has resting state. That has been recently much surfaced again with the discovery of the so-called default mode network, DMN, a set of regions mainly in the midline of the brain which exhibit high resting state activity. But how this intrinsic activity, which is pervasive throughout the whole brain, interacts with stimulus remains largely unknown at this point in time. But this strongly suggests that the brain itself, on the basis of its intrinsic activity, has a strong say in what happens in the brain when it is exposed to stimuli. So now you may say, why is all that relevant at all? You will see in the following that this is particularly relevant for mental features like self and consciousness. It may not be so relevant for purely cognitive processing, for instance, attention, working memory, etc. Those may all function without the intrinsic activity in a purely reflex-like way, as it is often presupposed to occur in neuroscience. However, mental features like self or consciousness or others like free will may necessarily require some intrinsic activity in the brain. Meaning, without such intrinsic activity, you might have neither a sense of self nor consciousness. You would be just your car standing in the garage or your bike. Whereas, due to the intrinsic activity, yourself is constantly moving back and forth and shifting. Okay. I want to provide in the following some evidence, empirical plausibility and evidence for that view, that the intrinsic activity is necessary and highly relevant for self and consciousness. Put in more philosophical terms, I will argue that the intrinsic activity first and foremost make possible a sense of self and consciousness. Like, without floor, you could not have any furniture in this room. Simply, the room wouldn't exist. Without intrinsic activity, you might have some furniture, but the furniture is no longer standing in the room, it's somewhere else. Meaning, you would have no consciousness of self. Let me go ahead. So, how can we study the self in neuroscience? As you know, the self is originally a philosophical concept, has long been discussed in philosophy, associated with mental features, the mind, the subject. However, neuroscience since 10-15 years, with the introduction of functional brain imaging, like fMRI, makes it possible to study it also in imaging, in the brain, in neuroscience. How can we do this? You can, for instance, compare stimuli which are very closely related to yourself with stimuli that are not so closely related. For instance, if you are from Ottawa in Canada, you know that there are long winters. They can be very long and cold. -30 degree, harsh wind from the north. Even end of March, as it is currently the case. So now, when you see a picture from Ottawa, 31st of March, -30, snowstorm, that picture is highly relevant for you. Because if it's not relevant for you, you will not survive. Period. Now, you're from Taiwan. You've never been to Canada, and no way. -30 is not for you. Now, you see that picture and say, this is absolutely not relevant to me. Rather, the coconut and the tropical climate are much more relevant for me. So you have different degrees of personal relevance, or what we call self self-relatedness. Now, you can compare high and low self-relatedness. Picture from Ottawa versus picture from Taiwan. Minus 30 degree versus plus 30 degree. Snow versus sun. You can present it once to a person from Ottawa in Canada and once to a person from Taipei in Taiwan. They will have opposite judgments of the pictures. But in both cases, you see probably a strong activity change in the cortical midline regions. These are regions in the middle of your brain, including several regions. The various studies on self-relatedness have indeed demonstrated that the cortical midline regions are very active during self-relatedness. This is the specific features where you see the coordinates, particularly in the midline regions. So, what do I mean by cortical midline regions? This is a set of different regions, particularly in the midline region, and it can be considered as an extension of the limbic system. You see here the medial orbital prefrontal cortex, perigenial anterior cingulate cortex, ventromedial prefrontal cortex, dorsomedial prefrontal cortex, supragenial anterior cingulate cortex, posterior cingulate cortex, medial parietal cortex, retrospinal cortex. And these midline regions seem to be anatomically an extension from the subcortical region and the limbic system to the cortical level. So the question is now, after the initial meta-analysis, which I showed you in the last slide, has showed that apparently self versus non-self stimuli make a difference in the activity level of the midline region. So what is so special about these midline regions that they seem to have a specific role in processing the self? So what I will show you in the following is how you can study the self and how we, for instance, do it. If the self is indeed so different and basic, your self is always with you. You know it. Wherever you go, even if you move from Canada to Taiwan to escape the winter, you may leave the winter, the minus 30 degree and the harsh wind behind you. But you will always take yourself with you. Even if you don't have an extra bag or suitcase for yourself will always be with you and will have probably no problems of passing the border. So how is it possible? So that means that your self is deeply somehow ingrained in your brain, and you're encoded, if one wants to say it in this way. So, and that also means your self is always manifest in the way you perceive things, the environment, how you feel emotions, how you experience your body, how you make your decisions, and also it is very much manifest in your consciousness, because without a self or a subject, you could not experience any consciousness at all. This is what the philosophers tell you. So, what I'm now doing is investigating the self in different functions and context. First, I will investigate the self in the bodily awareness. How is the self relevant for our body? So our body is part of our self. So how can we be aware of our own body? Then how does the self impact decision making? Then, as I told you at the beginning, there's an intrinsic or resting state activity in the brain. If the brain is always with us, the self. If the self is always with us, it must be somehow manifest in the brain's resting state activity. And finally, the most difficult part, and probably the most contentious, that how is the self manifest in consciousness? Okay, let me start with the decision making. You make daily decisions. Every day, at least 20 times. Whether you choose the flight ticket to Ottawa or to Taiwan, that's one decision. Whether you take the job offer in Beijing or in Rome, that's another possibility. Whether, even more simple, you go to the store, you buy the French cheese or the Canadian cheese, that's yet another decision to be made. And sometimes you look at the two cheese and you say, oh, the one is much more expensive, so I take the cheaper one, because you're short of money. So there's a clear external criteria. However, Now the two cheeses are the same price. No difference. So now it's just up to you to decide. It's your subjective preference. French cheese, Canadian cheese. Cheddar cheese, Camembert. Which one you take? Pure subjective preference. So in the one case, you can guide your decision by external criteria. The price. Different. In the other case, a subjective preference, it's called internally guided. So, and it is obvious that in the case of internally guided decision-making, yourself comes into play. So yourself is very important and serves as criterion to make the decision. Whereas in the externally guided, it is the environment which, along which you tailor your decision. So therefore, a former postdoctoral student of mine, Takashi Nakao from Japan, who is now back in Japan in Hiroshima, he was interested in the distinction between externally versus internally guided decision-making, environmentally versus self-guided or based decision-making. So he did a meta-analysis first of all studies which basically apply a design which is based on externally guided decision-making, whereas studies like moral judgment, which is rather based on subjective preference. So what he could demonstrate is that during externally guided decision-making, you had strong activity in the dorsomedial prefrontal cortex, and you can see here the dorsolateral prefrontal cortex, very typical, and parts of the anterior insular and dorsolateral prefrontal cortex. And he investigated it for uncertainty situations as well as for social situations. He had the same pattern. How about internally guided decision-making? When you rely just on your own self, just on the preference, Camembert, cheddar. So in that case, you have a typical set of midline regions active, like here's a posterior cingulate and the perigenial anterior cingulate cortex extending to dorsomedial. You can see these are the typical regions of what is called the default mode network, which shows high resting state activity and particularly low frequency fluctuations. So this is a typical pattern for internally guided decision making. He then looked for the overlap between internally guided and externally guided decision making activation patterns. The only overlap, signaled here in green, you could find in the dorsomedial prefrontal cortex. And you can see that the red is the internally guided, activates really regions specific for the internally guided, as distinguished from the externally guided here in blue. He then also, to be complete, he made a direct comparison and particularly look at here, externally guided versus internally guided. So all those activity changes which are larger in externally when compared to internally guided decision making. You see particular lateral regions and the dorsolateral prefrontal cortex. When he did the reverse comparison, internally guided versus externally guided, as I said, this is a set of studies, this is a meta-analysis, he found again these typical anterior, posterior, midline regions, perigenial anterior cingulate cortex, posterior cingulate cortex. The typical regions of the default mode network and the cortical midline structure. So that further underlines that somehow the self in decision making is manifest in activation changes in the midline regions, because internally guided is self-based decision making. So this basically, also when you look at the networks, you have different networks implicated. The externally guided seems to rather implicate what is called the task-positive network. Lateral cortical networks, executive control network, attention network. Regions like the dorsolateral prefrontal cortex, insula, thalamus. And this is basically, on the theoretical side, it's basically on outcome. And you have usually task with one or less predictable answer. For instance, it's clear if there's a difference in price between Camembert and cheddar, the answer is clear. Which one is cheaper, which one is more expensive is clear. So In the case of internally guided decision making, you rather have the task negative network, it is often called, the default mode network, strong midline regions, ventromedial prefrontal cortex, periginal anterior cingulate cortex, posterior cingulate cortex, and superior temporal gyrus. And typically you don't have a correct answer because it's subjective. Which cheese is better, the camembert or the cheddar? Subjective. For you it's the camembert, for me it's the cheddar. So it's purely subjective. There is no objectively correct answer. So, and interestingly, these two networks seem to be mediated by the dorsomedial prefrontal cortex. So, now the question is, how does this network mediate internally guided decision making? This has been a lot investigated in the literature. This has been rather neglected. So, as you may remember, particularly in these midline regions, which I showed here, everybody who's an expert on the default mode network knows that these regions show high resting state activity. Typical regions of the default mode network, high resting state activity levels with a high and strong degree of low frequency fluctuations. So why and how do they mediate internally guided decision making? So for that, the former Japanese postdoctoral student, Takashi Nakao, conducted an EEG study on internally-externally guided decision making. So in a very clever design, he used an activation task with with different professions. And in the and he presented them always in combinations. And some of them were presented more often, and some of them presented were less often. In the externally guided decision-making, subjects had to ask which of the two was presented more often. So it's a clear external criterion, the frequency of the stimuli. Let's say the accountant, here's a tax, when he sees this, here's a tax clerk, was more presented than, more often than the other one here. So that's a clear external criterion, which one is more often. So then, in the occupation preference task, he presented exactly the same stimuli, but now subjects had to decide which profession do you prefer. That's pure subjective. And of course, we adjusted also the income of all that was controlled for that. So which one do you prefer? Do you want to become a tax clerk or an accountant? Yeah. And then he also did the same for color preference. Which colors do you prefer? And what he also did is he measured a resting state EEG for 4 minutes, eyes open, eyes closed. Then he had an intertrial period, 1,000 millisecond stimulus onset, and then subjects had to make a response and got a feedback. So he could measure 3 components in EEG: stimulus-locked ERP, response-locked ERP due to the judgment, and feedback when you got plus or minus, or correct or wrong. So this is, for instance, you're correct, and here you're wrong. Here you do not get any feedback because nothing is correct or wrong. And we focus mainly on the stimulus-locked ERP. Okay. So now, here you can see the stimulus-locked ERP, and what you typically see is really an N200. During the decision, this is very typical. And here on the left, you can see the externally guided. On the right, you can see the internally guided. Each condition, you may remember, also had I didn't explain this in detail, had a small conflict and large conflict. And what you can see here is somehow a difference between internally and externally guided decision making. You see the blue here has a much larger N200 than the internally guided, which is rather low here. Yeah? So that already signifies there's a difference in this stimulus-locked ERP, this purely stimulus-evoked activity. The question is, where does this come from? So based on the hypothesis that maybe internally guided decision-making may be more related to the midline regions, in particular its resting state activity, where you have high resting state activity, he then correlated the N200 from externally guided decision-making with the resting state activity in the same subject. This is what you can see here. And then he correlated the degree of N100, the amplitude of the N200, with the power in the resting state in the different frequency bands. Delta 1 to 4, theta 4 to 8, alpha 8 to 12, beta 12 to 30, gamma 30 to 40 hertz. So, and what you can see here is on the x-axis is the power in the resting state. And on the y-axis, you can see the stimulus induced. This is the power in the resting state in the respective frequency band. And here you can see the amplitude of the N200 during the internal and or external decision making. And you can see that here in the externally guided, you do not see any correlation, any significant correlation between the power in the resting state and the task-induced or stimulus-induced N200. Whereas for the internally guided, you see highly significant correlation. You see the asterisks here. Basically, and these are electrodes for which I single out here the plotted the correlation graphs. And you can clearly see you have a strong correlation between the power in the resting state activity and the N200 during the task-evoked activity during internally guided decision-making. So that means, let me show you this slide, that during the externally guided decision-making, you rely on the stimulus, the external stimulus. You do not much recruit your intrinsic activity because the stimulus itself tells you basically where to go. So you can be lazy. You don't need to recruit yourself. Just follow the stimulus. Okay, the camembert is $5 higher, so I go with the cheddar. However, when the stimuli do not provide any criteria on how to make the decision, okay, both cheddar and camembert cost $10, yeah, then you have to recruit yourself. Then your intrinsic activity becomes relevant, and it comes in. And then you have a more, what you call it, internally guided decision-making. Well, basically, then yourself takes over. If the environment doesn't give you clues, yourself has to become active. Otherwise, like everybody of us, our self is rather lazy. Why be active if not necessary? And the brain apparently thinks, to put it into parentheses, apparently the same way. So this is a very nice example of how the intrinsic activity is related to internally guided decision-making and subjective preferences, which involve yourself. So every time when you have a strong personal preference, I would predict that your cortical midline regions undergo a lot of activity change and that they are recruited. Whereas if you don't have a strong preference, you just follow the external lines of decision-making, then your midline regions and your resting state is probably not much recruited. And yourself rather remains in the background of your decision. Meaning your decision is more objective rather than subjective. And as you know, for instance, in psychiatric disorders like depression or schizophrenia, you see very strange examples of highly subjective decision-making. Where you say, this is crazy. Why do you say it's crazy? Yeah, because it's so subjective that you can say, no, I cannot understand this. From an objective point of view, I cannot understand why the schizophrenic patients, despite knowing that it's a hallucination, he nevertheless pursues this hallucination and tries to talk to them. Yeah? So how is that possible? Something must be wrong in these disorders with the intrinsic activity and the subjective preference. Okay, so that's one example how yourself is manifest and at the bottom of your decision-making. And most interesting, and I will come back to that at the end of my talk, that yourself consists basically here in a balance between internally and externally guided decision-making. Sometimes the environment is stronger, sometimes yourself is strong. It's always a balance depending on the context. And which is neuronally probably manifest in the balance between cortical midline regions task-negative networks, and lateral networks like control-executive networks and lateral prefrontal cortex. Okay, let me give you another example of how the self is manifest in various functions. Your body. Your body is the closest, always yourself. Sometimes it aches, sometimes it hurts. You had a short night, you prepared for an exam, or you were out in the pub. Your body feels achy, but it's still yourself. It is your body. Philosophers or phenomenologists call this lived body, as distinguished from a pure objective body. It's your subjective experience of your body. So something like that we tested here in another study. So this was done by Christine Wiebking, who tested the shift between internal and external contents in our awareness. Internal contents is, for instance, like our own body in your consciousness, like the awareness of your heart rate. If you run fast or nervous before exam, you experience your heart rate as a strong content in your consciousness, even if objectively your heart rate is still the same, but your experience is subjectively strong. You have strong bodily or internal awareness. Whereas when you're really captured by this talk and you listen to this talk, the talk, your awareness and your consciousness is focused on external content. And your heart can do whatever it does not enter your awareness. Okay, so what she did, she investigated the external and internal awareness. She did a very clever study. So she looked at the heartbeat. So subjects had to monitor and perceive their own heartbeat and count the number of beats. Sounds difficult, but it can be relatively easily trained. And at the same time, there were also presented some tones. And sometimes subjects were asked to count the tones and perceive the tones and count them. So either your awareness was shifting between internal contents, your own heartbeat, and external contents, the simultaneously presented auditory tones. So, and then she compared all that in relation to the resting state, fixation cross. So fixation cross, larger interoceptive awareness and exoceptive awareness, heartbeat, auditory tone. And you could see this is a typical pattern you see in the midline regions. You see a strong decrease in activity level, so-called negative bolt response or deactivation, which is probably due to the fact that you have a high ongoing level of resting state activity in this midline region. The typical pattern. You see the perigenial anterior cingulate cortex, here called left medial prefrontal cortex, and the precuneus or the posterior cingulate. And you may remember these regions from before. You had them during internally guided decision making. Same set of regions. Now they're suddenly active during awareness of internal external content. So the most interesting thing that there was no difference here between heartbeat awareness and tone awareness, between internal and external content. Oh, this is strange. How is that possible, you may ask? Now I want to say maybe, doesn't brain distinguish between internal and external content? Come on. I know very well that this is the external world out there, the talk, and this is my own body. Oh, wait a minute. I remember my friend who's schizophrenic. Yeah, he cannot properly distinguish between internal and external content. So there must be some neuronal mechanism going on. Right. So now the question, how does the brain distinguish between internal and external content? And for that, between internal and external contents or between self and non-self related contents. How is that possible? For that, you may want to go to Japan, because there you find GABA. Wait, GABA is a biochemical substance you find everywhere, in every brain. So you find it in Japan. I found this in Japan. It's an advertisement, and it's called, the company is called GABA, and you see JP means obviously Japan. So now, what Christine Wiebking investigated, she investigated the GABA A receptors These are sort of the entrance doors for the GABA as a biochemical substance to enter the cells. So she investigated the GABA A receptors using a particular imaging modality, positron emission tomography, short PET, with flumazenil binding potential, and you call it the binding potential. And then she raised the question whether the degree of GABA and GABA A receptor binding is related to the degree of deactivation during internal and external awareness. And that's exactly what she did here. You can clearly see here, she plotted the GABA A receptor density, the binding, and linked that, what you can see here on the x-axis, and linked that to the degree of signal change in the fMRI, remember the deactivation. The blue is the extroceptive, is the tone, and the red is the interoceptive, the own heart. And you can see a correlation between GABA and signal changes only for the tone, the blue thing. That is significant. Whereas the red thing, the heart, is not significant. So that means that GABA apparently only seems to modulate signal changes during extroceptive, during external content, while internal content it does not modulate. That's very interesting, because you have, for instance, in patients with schizophrenia, you have indeed severe changes in GABA, and also in these regions. So maybe that is related to their confusion between internal and external content. For instance, they take voices which they hear as hallucinations internally to be external content. That's very confusing. How is it possible that you hear a voice inside your head and you say, no, 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 this is out there? So even in the absence of your friend, you still hear your friend. That's very confusing. Yeah? So maybe there's something wrong with the GABA. It's a confusion between internal and external content. That is, on a more general scale, what this study suggests. She then also did a whole brain comparison, put in GABA receptor binding in this region as a covariate for the whole brain comparison, fixation larger, extroceptive awareness, and you got again this region. The same for the perigenital anterior cingulate cortex. You see red curve, no significant, blue curve, external tone, significant. So it seems that the GABA seems to really mediate extro rather than interoceptive awareness and content. And that basically your body, which is yourself, but that is somehow distinguished from the environment. And maybe apparently the GABA seems to be central for that. That's of course a very tentative finding which we try to pursue in further studies, because it really seems to be the assumption is here that really GABA mediates the transition between internal and external content in your consciousness. And ultimately, internal contents are those contents which are close to yourself, like your own body. So basically, GABA seems to be central in mediating the distinction between self and environment-based contents. So this is obviously something to be discussed in the future. But here's a very interesting application. She did a further study and looked on the insula. The insula is a region in the lateral surface of the brain, and it's very important in the processing of stimuli from the own brain, from the own body, interoceptive stimuli. So now, what you could here see now here, that apparently here in the insula, unlike in the perigenital anterior cingulate, GABA seems to mainly modulate the interoceptive stimuli. So why is that? That's very strange, you might say. In the perigenital anterior cingulate, GABA was related to extroceptive contents, the tone. Now in the insula, it's related to interoceptive content, the heartbeat. So that may be related to the predominant input, which is more predominant. So here she could show that the more GABA you have, the stronger signal changes during the own heartbeat. So here it's the same, and this is very interesting because it's related to hopelessness. The more GABA you have, you can see this here, the more GABA you have, the less hopelessness. Whereas, and this is then also related, the more signal changes you have, the less hopeless you are. So meaning the more GABA, the more signal changes. So that's very interesting because, for instance, patients with anxiety disorders might suffer from abnormalities of GABA in the insula. So why is GABA so important? I showed you that GABA is prevalent in Japan, and it's also in China. So I found this in the shop. This is from China now. GABA. Here it is sweets, meaning in cookies. But what I'm really interested in is GABA in the brain. So why is GABA so important? Both GABA and glutamate are the major players in constituting what is called the excitation-inhibition balance. GABA is inhibitory and exerts an inhibitory impact and has a lot of GABAergic interneuron. Glutamate is excitatory, as you can see here, and excites. And the two together, the balance between excitation and inhibition between glutamate and GABA, shape and constitute what is called the excitation-inhibition balance. And that basically determines your level of activity, also in the resting state. So let me show this here. So this is the basic physiology. You have sort of a tonic, continuously ongoing inhibition of GABA, which is called tonic, is here the blue. Let me neglect this for the sake of simplicity. Then you have GABA. Then you have glutamate. It's the green thing. Here you have resting state. You have some changes, but not much. And then the stimulus comes, and then you have an increase in glutamatergic excitation. And at the same time, you also have an activation of your GABAergic inhibitory interneurons by the pyramidal cells of the glutamate. So that means, and then you have a change in your excitation-inhibition balance. You have inhibition, but also excitation, and also there's a slight temporal delay between activation of the GABAergic interneurons and the pyramidal excitation. So, and this is basically what leads to the kind of neuronal activity. So the question is here, and that's something we really don't know these days, how much this excitation-inhibition balance on the regional level has functions according to the same principles as the cellular level. So the other question, this is basically this one here, and how apparently also the stimulus interacts with the ongoing excitation-inhibition level and GABA and glutamate in the resting state. We simply don't know these days. Then the question indicated by the study with the tone and the heartbeat, does GABA mediate regionally and specifically psychologically affect? And how does it mediate the transition from resting state to stimulus-induced activity? How about glutamate? Does it modulate cortical-cortical activity synchronization with functional connectivity? How about the resting state? We conducted a series of different studies to understand a little bit the physiology of the excitation-inhibition balance and GABA and glutamate on the regional level. Why is that important? Because if we understand that, we might a little bit more better understand how the self and non-self related stimuli can be distinguished by the neuronal activity in the brain. So basically, if you can say that the distinction between self and non-self, I showed you a little bit here with internal, external content, how is that related to the self? And if already the distinction between self and non-self is encoded in the activity on the biochemical level, on the level of GABA and glutamate and the excitation-inhibition balance, it really tells you that the self may be an essential component in structure and organizing neuronal activity. So that ultimately leads us to the thing now you might want to say, where then is the self located? Everywhere and nowhere? Yes, I think one can almost say this. One of the hypotheses we have is that the cortical midline structures and the subcortical midline structures here are somehow very closely integrated. That's basically the extension of the subcortical limbic system on the cortical level. And that seems to mediate self-related functions. So now, and it is interestingly in particular this set of regions that you have a strong and high resting state activity. This is the core of the default mode network. So the question is now, if these regions are always recruited during self-specific stimuli, how is this then related to resting state activity? So Pengming Qin from China, he did a meta-analysis on studies, and he observed that there's a strong overlap between regions of the default mode network and regions activated during self-specific stimuli. And most interestingly, that you do not have much change of activity during self-specific stimuli when compared to the resting state activity in these regions. So meaning, particularly these regions, you have a high intrinsic activity level, and then a self-specific stimulus like your own name comes, and the activity of these regions does not change. This is very strange. Because usually you would expect, of course, any kind of external stimulus should change the activity in the brain. Here, it doesn't. That is very strange. So, how can we investigate it? And this means maybe there may be special forms of the interaction between resting state activity and stimulus-induced activity, what we coined rest-stimulus interaction. So the resting state might have specific features, and there must be some information about the self encoded that self-related stimuli like your own name, or for somebody from Ottawa, a picture of -30 at the end of March, interact in a specific way with the resting state than non-self-related stimuli. So Pengming Qin conducted a very clever study. He investigated the sensory cortex, particularly the auditory cortex, when listening to your own name and another person's name. So he had 3 kinds of stimuli: subject's own name, familiar name, like the prime minister of your country, and unknown name, like the prime minister of another country you've never heard of. Then he also measured the resting state activity during eyes open and eyes closed. 5 minutes eyes open, 5 minutes eyes closed. And then he presented the stimuli, auditory stimuli, own name, familiar name, other name, during eyes open and once during eyes closed. So the eyes open and eyes closed condition basically served as indicators of different resting state activity levels. And we showed this here. In eyes open, eyes closed, you see a significant difference in activity change between eyes open, eyes closed. So you have higher activity during eyes open, during eyes closed, when compared to eyes closed. Why? Because your visual cortex gets activated and it sends some activity to your auditory cortex, cross-modal interaction, and your auditory cortex also becomes more active. So, and then he investigated the 3 stimuli during eyes open and eyes closed. Here you can see the red line is eyes open, and the black line is eyes closed. Now, the unknown name induced the same stimulus, induced higher activity during eyes open when compared to eyes closed. Of course. No wonder you will say because of this difference between eyes open and eyes closed. So, in more scientific terms, this seems to be a purely additive interaction where the stimulus-induced activity is superimposed upon the ongoing resting state activity. Okay, next one. Familiar name. Same pattern. Seems to be a purely additive or superimposing effect where the stimulus-induced activity is just overlaid or superimposed upon the different resting state activity levels. This difference is due to this. Now, in subject's own name, you don't see this pattern. You don't see any difference between the subject's own name presented during eyes open and eyes closed. This is very strange. Because you see a clear difference, eyes open, eyes closed. The self, and you see this in left and right auditory cortex. Apparently the self does not care. Whether there's higher or lower resting state activity in auditory cortex, the own name just induces activity change. Independent. It doesn't care. That's from a purely stimulus view, this is very strange. So there seems to be some special features in the intrinsic activity which somehow recognize the self. Let me give you a typical example from the real world. You probably have heard about the cocktail party effect. The cocktail party effect signifies that you're in a party in a very busy room. You're on a party, everybody talks, and you barely can hear the other people's voice. You have no idea who's talking what, and names are going back and forth, and you don't understand anything because it's so noisy. Suddenly, somebody in the opposite end of the room utters your name. You hear it. In the midst of the cocktail party, everything is busy, you hear your own name. So somehow your auditory cortex seems to be somehow primed to detect your own name. I think these results can contribute to that. So what does this tell us about the concept of self? Usually, the self is considered to be a higher level function that results from cognitive, as the integration from cognitive, sensory-motor, affective, and also social functions of the brain. So usually the self is located here. However, these results seem to speak a different language. They seem to suggest that self and resting state activity somehow very closely overlap. That there's some information encoded in the resting state activity about the own self and self-specific stimuli that let the resting state react in a different way to self-specific stimuli, like the own name, when compared to others. So, for instance, when you, being from Taiwan, see a picture from Ottawa, -30, end of March, your resting state does not recognize anything in that, because you cannot relate to that. If in contrast I see this picture, I can relate very well to it, and my resting state contains some information that recognizes and lets it react differently. What did I show you so far? So far I showed you how the self is manifest in decision making, in body awareness, and in the resting state. Now I show you yet another puzzle. How is the self manifest in consciousness? You sit in front of this video. I hope you examine it consciously. Your level of consciousness is high. You're aware and you focus on the external contents, meaning the talk. What you experience is the talk. But suddenly, you switch your focus. Suddenly, you have a sudden pain in your head. All the focus is taken away from the video to your own self, the subject of your consciousness. So your subject, your own self, is either in the background or in the forefront of your consciousness. And without subject or self, you would not have any consciousness. Every philosopher tells you. So the concept of self has often been intrinsically tied to the concept of consciousness in philosophy, in particular to the reflection. I become aware of the contents of my consciousness, and I become aware that it is my subject, that I as subject experience consciousness. And that awareness of consciousness and the subject of my consciousness yields what they call self. This is what often called reflective self. It goes back to Descartes. It's very much prevalent in current cognitive determinations of the self. Then phenomenological philosophy said, no. Any kind of consciousness comes by default with some kind of sense of self. So it's basically always already there. In the same way that any chair comes with a lean. You cannot avoid it. So any consciousness comes with the self. So you don't need any kind of reflection to get a self. That's what they call pre-reflective self. Husserl, the founder of phenomenological philosophy, a current philosopher, Dan Zahavi from Denmark. So meaning that consciousness implies the self. So this raises the question, and they focus more on sensory motor functions rather than cognitive functions. Maybe because of sensory motor processing, the self is always somehow implied by any kind of consciousness. So now the question is, how can we tackle this issue of the relationship between self and consciousness in experimental ways, like in neuroscience? So one way is, for instance, to investigate patients with vegetative state. Patients with vegetative state or coma have lost their consciousness. They are by definition non-conscious. They don't move, usually. They may blink their eyes. They don't speak. They do not show any signs of consciousness, but they're still alive. Usually, often young people after severe motorbike accidents or car accidents. The most prominent example these days is Michael Schumacher, the former Formula One driver, who is, after a ski accident, end of last year, in a vegetative state. So how can you test the relationship between self and consciousness in these patients? Peng-Ming Kim and another postdoc of mine came up with the clever idea of presenting self-specific stimuli, like own name or autobiographical events. And what do these stimuli induce in these patients' brains? So here's the first study. Peng-Ming Kim presented the own name and a familiar and an unknown name to the subjects in vegetative state. And what he could observe, to his surprise, that all these patients, you can see here's a single patient, still exhibited some neuronal activity change in response to the own name. Particularly again in the midline regions, like here in the anterior cingulate cortex, the caudal anterior cingulate cortex. And most interesting, he could find also in other midline regions. This is a summary slide of all patients. You can see here the typical midline regions, which you already have seen quite a number of times on the different slides. And you also could see that patients in a minimally conscious state, you have somehow a level of consciousness and arousal, show higher degrees of neuronal activity in response to the own name. Most interestingly, this is also documented in the correlation between consciousness and degree of neuronal activity. The higher your degree of neuronal activity in response to the own name, the higher your degree of consciousness, particularly here in the anterior cingulate cortex. So this is first scientifically very interesting because it suggests some kind of relationship between self and consciousness, that maybe your degree of self-relatedness and associated neuronal activity drives your degree of consciousness. And clinically, this is very interesting because it suggests that maybe the self-related neuronal activity could be a clinical predictor. So then we conducted yet another study, and this was another Chinese postdoctoral student of mine, Zirui Huang, who, rather than presenting the own name, he presented autobiographical questions. This was done in China, so for instance, have you been to Beijing? And he compared that with non-self-referential question, is 1 minute, 60 minutes, auditorily presented, obviously. And then he compared the self-referential versus non-self-referential activity. And he did a comparison between the healthy and the vegetative state patients. And what you can clearly see, you still see some neuronal activity change. Here the green curve is the healthy subject, the blue curve is the healthy subject. Non-self, self. These are the patients. You can see the difference between the healthy and the patient was mainly again in the cortical midline regions, the perigenital anterior cingulate cortex and the posterior cingulate cortex. So you can see clear, again, these midline regions differed between the VS, the vegetative state patients, and the healthy patients. And you can also see that there's still some activity, particularly in the minimally conscious state. So now the question is, how is this neuronal activity related to the level of consciousness? This is shown here. You see here on the x-axis the degree of self, non-self differentiation in neuronal activity. And here you see the degree of consciousness measured by the consciousness recovery scale. And you can see that the higher your neuronal activity during self, non-self, meaning the higher your degree of consciousness. And this is again the perigenital anterior cingulate, posterior cingulate cortex. So this confirms the previous finding and tells you that maybe the degree of neuronal self, non-self differentiation, the degree of self, non-self differentiation tells you something about your degree of that your degree of self, non-self differentiation drives or predicts your degree of consciousness. So this sheds some interesting light on the relationship between self and consciousness. However, you may remember that the intrinsic activity, the resting state activity in these midline regions, like the PACC and the perigenital anterior, is very high. So what Zirui Huang investigated, then also the resting state activity in these patients. He investigated the functional connectivity, short FC, from the posterior cingulate cortex to the anterior cingulate cortex, and vice versa, the other way. And you can see again severe deficits in functional connectivity between patients and healthy subjects. So meaning the communication between regions, the functional connectivity is significantly lower in the patients. But most interesting, he also investigated the variability, the degree of change, the spontaneous change in these regions' neuronal activity. So and what he could observe is that this is hidden under the meaning of the amplitude of low frequency fluctuations, the temporal variance, or the degree of change in the spontaneous resting state activity. And you could see again a significant difference in the midline regions, in the posterior cingulate cortex, in the perigenital anterior cingulate cortex, meaning that these regions seem to show significantly lower degrees of change in neuronal activity in vegetative state patients. Meaning the car is no longer as moving back and forth in your garage or your bike as in the healthy case. It's sort of more stationary, it takes more the same position. There's not much as change anymore. And most interestingly, the degree of change, here the ALF, amplitude of low frequency fluctuations, here on the y-axis, predicted the degree of stimulus-induced activity, self, non-self. The more variability you had, the higher your degree of activity difference between self and non-self. So higher variability predicts a better differentiation between self and non-self. And you remember that self, non-self, in turn, predicted the degree of consciousness. So you have a threefold relationship. Resting state activity, variability, predicts the degree of self, non-self, task-evoked activity, and that in turn predicts the degree of consciousness. So it's like in a room. Your resting state activity and your variability compares to the floor. Your task-evoked activity compares to the legs. And the degree of consciousness compares to the plate on the legs, which then shape a table. So how can we imagine this in more concrete terms? You have high resting state activity, in particular the cortical midline regions. That resting state activity seems to be mediated by an excitation-inhibition balance, by GABA and glutamate, as I indicated in the earlier slides. In addition, this resting state activity somehow seems to encode some information about the self, which I called here self-specific organization, which is so completely unclear at this point in time. You remember the studies on the auditory cortex and the different levels of resting state activity, eyes open, eyes closed. And with that, resting state activity is modulated by external stimuli. You see the big red arrow is the resting state activity with these features. And that is modulated by the external stimulus. That induces some rest-stimulus interaction. And if that rest-stimulus interaction occurs the right way, then you might have consciousness of that external stimulus. So you might assign or attribute consciousness to the stimulus-induced activity related to the external stimulus. And at the same time, you might also have a somehow sense of self, which may remain in the background, the subject of your consciousness. Because without subject, you could not experience any consciousness at all. This is what the philosopher will tell you. So, this is a model which is somehow, so here you can see that I attribute a central importance to the brain's resting state and its intrinsic activity. It's basically at the bottom, the very ground upon which any subsequent stimulus-induced activity stands and which makes possible the assignment of consciousness to the stimulus-induced activity. If you had no such bottom, you might still have a chair. If you had no floor, you might still have a chair, but the chair might be somewhere else. But with a floor, the chair can stand and the whole room sets up. And then you can have consciousness. In the case of the brain provides a particular input, its intrinsic activity. And that input is necessary to assign consciousness to the task evoked or stimulus-induced activity. That's very reminiscent of a model of the mind suggested by the philosopher Immanuel Kant. So he suggested that the mind provides a specific input, a particular structure by means of which the incoming stimuli are structured and organized. And that in turn, that organization and structure makes possible a consciousness and self. So, I come towards the end of my talk. I told you a lot of slides, data from imaging, and what it tells us about the self, its relation to the brain. I showed you that the self is manifest in different functions, that you can scan that. The exact mechanism of how the self is encoded in resting state activity, how it impacts and manifests the various functions like decision-making, body awareness, or consciousness remains unclear at this point. We simply do not know. So now, what do I mean by concept of self? This is a conceptual question. It can be answered on the basis of empirical data, but it needs a conceptual investigation. So, and that, of course, what is the concept of self? As I said, it's a conceptual question. So, what I consider based on the data I show you, that the self is not a particular entity in the brain. It is rather a specific form of organization, a spatial and temporal organization of the resting state activity, which the exact features, the spatial and temporal features, really remain in unclear. Spatial features, for instance, in the functional connectivity, temporal features, for instance, in the various low and high frequency fluctuations of neuronal activity in the resting state. And most important, it seems to consist in how stimuli from outside the brain, from the body or the environment, are related to the brain's intrinsic activity. So meaning, the stimuli from body and environment are set and processed in relation and relative to the ongoing brain's intrinsic activity. And in order to be effective, these extrinsic stimuli must be somehow integrated and linked to the brain's intrinsic activity. They must be organized and structured by the brain's intrinsic activity, spatial temporal structure. So what then is the self? The self may be a sort of mode or form of neuronal organization, which makes possible the processing of stimuli from outside the brain in relation and relative to the ongoing brain's intrinsic activity. So this means the self is not some kind of mind or metaphysical entity or a specific cognitive entity. That means the self is so closely related to the resting state and self-specific organization must be manifest in all kinds of different functions. I showed you decision-making, bodily awareness, rest, and consciousness. We have other studies where we linked self to reward, where we linked self to emotions. And other studies are in discussion to link self and attention. Because indeed, if the self is basic, it should be everywhere and nowhere. It should have its fingers, as we say in German, in any function. So that means the self is a basic function. It's not a higher order cognitive function. And that maybe it's a continuous process of neuronal organization. Your spatial-temporal structure of your intrinsic activity continuously changes and aims to adapt to the respective environmental context. And that in turn changes yourself. We all know this. So the self is everywhere. It seems to be a default mode of the brain. The brain cannot do without constructing something which we experience of sense of self. Apparently, it cannot relate to the environment other than by constructing some kind of self-related processing and hence a sense of self. So that means self is like GABA. You can find it everywhere. I told you you can find the GABA not only in the brain, but also in China and Japan. You remember the previous slide. The self is everywhere. I found the self at a train station in Milano, in Italy. And trust me, you find the self everywhere. The self is like a bar without which you cannot eat anything. So, let me just sketch in my final slides some difference. I sketched it here for consciousness. The same holds true for self. So consciousness and self have often been regarded as higher order functions. The highest pinnacle, the highest level of integration. So that has been associated with cognitive functions and task-evoked activity. Often some other approaches with affective functions or sensory-motor functions, but always with integration and task-evoked activity. The data seem to speak a different language. You do not have to start with the functions. You have to start with the intrinsic activity and its spatial-temporal structure. And that provides a predisposition for self and phenomenal consciousness. And upon that, the various functions are then built, like sensory-motor function, affective and cognitive function. And that makes perfect sense, because any of these functions, like perception on the sensory level, action on the motor level, emotional feelings, cognitions, all take place within the space of consciousness. You always have a certain experience, a subjective experience associated with your perception, with your action, with your emotions, and with your cognitions. It is always, as the philosophers like to say with Thomas Nagel, what it is like to have a certain cognition, what it is like to have a certain emotion, what is it like to have a certain perception or action. So the question is, that really leads you back to the very bottom, that self and consciousness are at the very bottom, and they basically provide the ground. And that is well reflected in the brain's intrinsic activity. And now, what then actually is the self? It's a virtual, if you want to say so, a virtual spatial-temporal structure that structures and organizes neuronal activity and how it relates to the environment. So if you want to speak the latter, it's a self-related or rather brain-related processing. How stimuli from body and environment are related to the brain's intrinsic activity. And that relation structures and organizes any subsequent neuronal activity. So that ultimately leads you maybe that the intrinsic activity provides a key to the brain. In particular, a key to the brain's ability to contribute to the construction of mental features like self and consciousness. So maybe the intrinsic activity might be a key that could unlock the brain and ultimately consciousness, as I discussed in these 2 recent volumes that came out at the beginning of the year, Unlocking the Brain, Volume 1 Coding, Volume 2 Consciousness. Thank you very much.